Hello everyone. Thanks for coming to our presentation of our work Canopy Graph Embedding for Recommendation via Conditional Proximity. I'm Kachun Lo, and this work is done by me and Tsugasai Shigaki. We are from Tokyo University in Japan. And here's the outline of today's presentation. And we'll first introduce our works by talking about some preliminaries, challenges, and as well as our contributions. Well, our work is about building a recommender system, and recommender systems seek to effectively connect these entities, whether it is a user or an item or other information, by providing recommendations. And recently, user-item bipartite graph has been studied and exploited to learn representative embedding for personalized recommendation. Especially graph-based approaches involve a model with the capability of capturing complex information flowing from indirect neighbors to source node. So the main objective of our work is to try to learn better user item representations for better recommendations by fully exploiting the connectivity information from bipartite graph. And some limitations of previous works includes, first of all, treating indirect high-order proximity in the same way as direct proximity and ignoring the intermediate nodes. Secondly, a lot of weighted extra parameters are introduced in training or inference in most graph-based collaborative filtering models, which makes the models to be very slow and hard to update on a more frequent basis. And compared to the popular node level attention, feature level attentions has not been utilized in graph embedding studies, especially in the recommender system area. So given these observations, we propose Canopy, a collaborative filtering graph model where information flows are conditional on intermediate nodes to learn useful representations for user and item representations. The main contribution we have made are, first of all, we propose Canopy, a lightweight graph-based collaborative model for recommendation, which gets rid of additional parameters, achieving fast inference and allowing easy construction and being less prone to overfitting. We also proposed a concept called conditional proximity to model the decisive process that before arriving to source nodes, information signals are first filtered and enhanced by intermediate nodes. Especially feature-wise feature level attention is used to capture such conditional dependencies. And finally, we also conducted extensive experiment to show the effectiveness and superiority of our model over state-of-the-art models. And here we talk about some details of our model. And especially in this presentation, we will focus more on a intuitive level rather than go deep into the equation. So the overall structure is illustrated like this. Canopy models high-order information proportional information propagation conditionally. The process that information has to flow through intermediate nodes before arriving to source node is modeled as conditional proximity, and we design a feature level attention mechanism to capture such conditional dependencies. So what is conditional proximity? Well, indirect neighbors have intrinsically different ways of propagating information from direct, which is one-order neighbors. Therefore, intermediate nodes which connect source and the end nodes play a decisive role in high-order proximity. Illustrated below, a two-order neighbor, user 1, has two paths to the source node U2, where each path carries fundamentally different information depending on exactly the intermediate node I1 and I4. So intuitively, suppose, let's say you have two friends, a scientist and an artist, and they both recommended a book to you. Well, you'll probably be very interested because the books get multiple suggestions from two of your very close direct friends. However, more interestingly, you might perceive the two suggestion messages very differently. While the scientist friend might give suggestion for educational purpose, the artist friend might recommend this book because of its aesthetic value. Well, we therefore refer to this information propagation being conditional on intermediate nodes as conditional proximity and the intermediate nodes as conditional nodes. And for first order proximity, following previous works, the proximity score between a source node and its direct neighbor is simply measured by the dot products of their embeddings. And so more interestingly, for high order proximity, for example, for a two order proximity, unlike direct neighbors, we model high order proximity as conditional proximity, where the intermediate node is taken into account as condition. We denote the conditional proximity between the source node and its second order neighbor as below, where the I is the intermediate node connecting the source node and the end node. Also, to model this proximity of U and AI3 given I, and to emphasize the effect of intermediate node, we propose to employ the feature level attention mechanism. Ideally, such mechanism should first aggregate features information from both source node and intermediate node, and then guide the information flows to focus on this important feature or these important channels in the embeddings. So a general proximity notation are shown as below. To simplify the notations, we use a generalized notation as follows for both conditional, high order, and unconditional, which is one order, which is first order proximity. So, and after we have the equation for computing proximity, we also propose three components to reinforce such proximity during training. So, which is quite, I guess, quite common in a graph-based model. So the first thing is called a length-aware decay factor, which simply say as the strength of proximity decays as the order gets higher. So we take into account such effect by integrating a length-aware decay factor, where the k is simply the length of the path. And the second component is called out degree aware factor. Moreover, nodes out degree also plays a very important role in measuring user items relations. Given a node J, its importance would decay as if it's too popular or it has too many out degree levels. And finally, we also have a special sampling methods called extended random walks to reinforce the conditional proximity without missing any meaningful neighbors. We use a straightforward extended random walk. The training example are simply connected by sampling data greater than one indirect neighbors in each step. In experiment, this step is done in pre-processing, so it wouldn't affect the training speed too much. And the optimization is based on a Bayesian pairwise ranking loss function, BPR, which is a very, very popular loss function in recommender system. It utilizes positive and negative example to affectionate to make the training process more effective, more efficient. And we have also done some experiments. The dataset we selected are some public datasets called Amazon Book, and another one is called Koala. And here are some baseline models we used to do comparative experiment. And here's the comparative experiment for Hanabi. And best results are in boldface, and the special symbol denotes the best baseline results. And we also done a ablation study to evaluate the effectiveness of each component. As shown below, experiment are on Amazon Book, and this base model is BPR. So we start from a BPR baseline model, and we add components on it gradually to see how they affect the performance. And it shows that the full Hanabi model tends to have better performance. In future, there are some direction to further explore. For example, we can extend Hanabi to a general graph embedding model, not just for recommender system, but also as the concept of conditional proximity is really a general thing for graph analysis. Secondly, we can also further examine the effects of each components in Hanabi. And finally, to include these other knowledge, for example, text or demographic data for a even better or personalized recommender system. And that's all about today's presentation. Thank you very much.